cool. So I want to share my screen. Could you enable me?
Sorry for that. I think you can share your screen right now.
Okay, cool. So are you able to see this?
Yes, great.
Okay, cool. Yeah, thank you, Julie, for the introduction. And so my presentation topic in this week will be about the modeling of building energies. So basically, the presentation will consist of 2 parts and a very brief self-introduction, and also mainly it will be about the introduction of building energy modeling. So my name is Chen, and currently I'm an assistant professor at the Department of Civil Engineering. And I've joined 1.5 years ago. And my major research direction is about smart built environment, including the grid interactive efficient building. And of course, we get increasingly amount of renewable energy penetrations, and we want to do some demand response so that we will be able to better adapt to this high penetration of renewable energies. And I've also done researches regarding the sensing of the built environment, like the envelope tracking, using some thermal cameras and advanced sensing techniques, or maybe some smart building operations like sensing of the occupancy, so that we can operate our buildings, based on different occupancy patterns. I have done some research regarding the occupants' comfort and health. And the other my major research interest is about the urban scale energy modeling and management, so that it can be a topic that is coupled with the distributed energy resources. Well, before coming to University of Utah, I was a postdoc at the National Renewable Energy Lab and doing some grid interactive efficient building research that we have applied different modeling generates the building load profiles of group of residential buildings, in a really large scale. And my research aims to develop this smart, sustainable, and resilient built environment, using different computing and sensing techniques, such as this artificial intelligence, modeling and simulation, and also Internet of Things technologies. And my background is actually quite computing, and if you are interested in any type of this building related or energy related or computing related research, and yeah, please contact me for that. So for the main topic today, it's about building energy modeling. So we know that building energy modeling is just a process of building a virtual replica of the buildings with its physical characteristics, so that in the past, we said that we want to perform the physics-based simulation, for the building energy use and also the indoor dynamics. But especially I think for recent 5 years, and the data-driven building energy modeling has become another branch of the topic that a lot of people are interested in. But here, when we talk about building energy modeling, we typically refers more to the physics-based simulation of building energy use and indoor dynamics. And generally in a BEM process, so building energy is kind of can be short for BEM. And we want to firstly idealize our building systems, and also our that we can have all derived and simplified physics rules, that we will apply and rely on, in this simulation process. Then what we want to do is, we want to establish the mathematical abstractions, basically just establish different equations, for all of our buildings and the systems with its physical parameters. And then we want to build the computation model so that we want to come up with a method so that we can solve all these different differential equations simultaneously, to get the result of what is the energy and also what is the temperature fluctuations, for example, for you simulated indoor environments. And finally, the last step will be just aggregates of the outputs, for all of our simulation results to any things that we are interested in. And it's very worthy to mention at the beginning that we don't want to mix this or mistake this building energy modeling process with the reality, because as getting through all this like idealization and also the abstraction process, a lot of information will definitely be missing in the process. But this doesn't affect that building energy modeling will still be a very useful tool for us, as said, almost some, but useful. And this building energy model is definitely useful for us. And the major use of the building energy modeling will include, firstly, to support the architecture design here, so that the architects can use building energy modeling to design more energy efficient buildings, and specifically, they can utilize this building energy modeling tool to inform any quantitative trade-offs between the initial cost of, for example, also the operation energy cost. And it can also be utilized to support the HVAC design and operations. Because BEM can be very helpful to the mechanical engineers, to design HVAC systems to meet different thermal loads more efficiently. We design different and test the different control strategies, for the HVAC systems, especially for very large and complex commercial building projects. And it can be very helpful for the building stock analysis. So for which we can perform a lot of analysis on the prototype models to support the development of the building energy codes and the different standards, or maybe help different organizations like utilities or maybe governments plan for large-scale energy efficient programs. And this is also a very important aspect that we have applied BEM for, because you will see a group of researchers in the national lab, and they are specially utilizing this building energy modeling tool to come up with different policies and also standards. And they are trying to upgrade or maintain the standards every day, based on the simulation results, with certain benchmarking. And finally, the BEM is very useful, for the rating of the building performance, and it just can be utilized to assess the performance of different buildings, such as for the code compliance purposes, or maybe for the green certification purposes. It will be one very good example of that, using BEM for the performance rating. Is this LEED certification process, and so LEED is developed by the USGBC. And they just get different levels of the certification. When you get points, according to the LEED criteria, then your building can either be kind of just certified, silver certified, gold certified, or platinum certified, which means that you will get points of 80 out of these 100. And if you see like the biggest aspect here, that is about the energy and the atmosphere, and it definitely requires you to optimize your energy performance. And for specific for this category, you will have 35 points, and actually 20 points of them is related to the energy modeling. And they want you to analyze different efficiency measures during the design process so that you can take all these into account in the decision making and try to optimize your building performance. So that's a very good example of where we typically apply our BEM tool for the building performance assessments or building performance rating. And it could be more than that. BEM is definitely a very multi-purpose tool that it can be utilized for all of the purposes that has been listed here. We have introduced the architecture design, the HVAC design, the asset rating, the policy analysis, and it can be also utilized to for some financial incentive purposes, such as for the energy saving performance contract, so that you will kind of have a contract with the other parties, and they will provide you with some energy saving measures in free, in the beginning. But later, if it proves that it will save you energy, then you just give some money back, gradually, in a kind of way of the cash flow. And definitely, you can utilize BEM for the retrofit design, for the control purposes, model predictive control. I think that is the most common advanced control strategies that we typically rely on, in the smart building control for the measurement and verification code compliance. So it's a really multi-purpose tool, and it can be utilized actually in all of the phases of building projects, like starting from the planning, and we can utilize BEM for the very early design phase of a building project, so that we can use BEM to evaluate the different conceptual design. And actually, just I think we don't want to look down upon this phase, because typically the earlier decision that we make regarding a project, large impact it will be, for the decision to have impacts on the building performance. So that's, we run some very simple, like building energy models, in a very early phase, in the conceptual design, and it will actually help us a lot, in the overall design of the building to improve the relative performance. And definitely it can be also utilized in the detailed design phase, so that we can run BEM models with more detailed measures, so that it will help refine our conceptual design, and also to support some like HVAC selection, or maybe support some value engineering process. For the construction, maybe that's the phase that BEM can be applied the least, so that we can utilize BEM to ensure the inclusion of all energy efficiency measures. While for the commissioning, we can utilize BEM to serve as the baseline model to just inform the commissioning process, to help us identify where cases that is unexpected, or in the operation and maintenance phase, and to verify the performance for the code compliance, or even some more advanced topics that we can utilize BEM, to support our intelligent building operations, such as the smart control or automated fault detection and diagnosis. While in the renovation phases, definitely we can utilize BEM to help us evaluate different refit options with life cycle cost analysis. And I think this is also one of the most common places that we typically apply building energy modeling. Yeah, so BEM has been shown to have the advantages of reduce the cost, and to help us design better building, with improved energy efficiency, and also with improved building operation and support value engineering. So with a better building, and then we will also have improved occupant satisfactions. So generally, so it will become a little bit more technical. And the building energy modeling it's kind of built on the heat balance of the building, since all this modeling will definitely need to apply the physics laws. So if you just think about the indoor air nodes, as air balance node here, and then the heat balance of the building that the building energy modeling will build on will incorporate mainly 3 aspects. The first aspect is we want to consider the influence of our weathers. That includes the temperatures and also the winds and the solar radiations that will impose a lot of loads on our buildings, through different modes of the heat transfer, like the conductions, convections, or maybe radiations. And it's kind of moderated by our building envelope, but it will influence the heat balance of our indoor air nodes. And the second aspect that we want to consider about that plays a lot of roles in this building energy modeling, is the internal heat gains. That is coming from our occupants and also coming from different appliances, like the computers you are using in the indoor environment. While the third aspect that we want to consider about for this heat balance of the indoor air nodes, will be the energy inputs from our HVAC systems. So that this will be the 3 main aspects that we want to consider as the heat balance. That is the basis for our building energy modeling process. So considering this heat balance, you can expect that our major 3 categories of the inputs when we perform the building energy modeling will be firstly related to these building physics properties with the external disturbance. So that it is specifically we want to kind of input the physical properties of our buildings, like the geometries and also different zonings for our buildings. And then we definitely want to input, also very importantly, the envelope properties of our buildings. And then finally, we want to input this external disturbance, as part of the inputs for our building energy modeling process, like what is the temperature of the exterior environment and what is the solar radiance, in different periods of time. And the second categories of the inputs, major categories of the inputs for the building energy modeling process is about this human and it is interaction with the buildings. So that it mainly includes, how we utilize or how we use different building systems, such as, what is the occupancy, because this is related to the internal gain, right? And then what is the lighting systems that we have installed and how we utilize that, or what is the plug loads that support our daily activities inside our buildings. And it also incorporates the settings of our systems, like how you want to control your HVAC, so how you want to adjust your thermostat. So that's the second categories of the major inputs for our building energy modeling process is the human interaction with the buildings. While the third category is actually our building systems. And we want to consider, different, we want to input what are the systems, especially like for the HVAC that has been installed for our buildings, what is the air handling units and what are the primary energy systems, chiller and boilers. And we want to also incorporate the inputs such as this water heating, lighting usage, refrigerations, and also if we have any renewable energy installed for our buildings. And also shading systems, that's also very necessary part because it will have a very large impact for the solar gains. And then finally, different control strategies for our building systems to serve the building loads in the building energy modeling. So this is for the very brief introduction of the whole calculation process. And generally, on the first step in the building energy modeling calculation process, we want to consider, this building and also system as the inputs, and also the weather as the inputs. And the building and the system here more represents the geometries and also the different building physical characteristics, such as the characteristics of the envelopes, and also what is our lighting systems, or maybe some other appliances that we have utilized in our buildings. And then with these two, and also we consider about the weather, then we can calculate the heat balance, and then we can simulate what is the load that is required for our indoor environment to reach a certain status. And then based on the building loads that we have calculated, then for the next step, we want to refer to our system inputs. So typically this is about the air handling unit and also the distribution systems here, so that we want to check that whether our system have enough capacities to meet all these building loads, and also based on different system types and configurations. Like we want to calculate in this case that how much volumes of the heating and the cooling air that is required to supply different building zones to reach different indoor environment conditions that is specified by the users. While after that, the next step is we want to perform some plant simulations, so that for this it will be more about like what is how our chillers and the boilers, or also the cooling towers, and also different pumps or heat exchangers that we will utilize to support, to kind of condition this air, so that this will be more on the primary energy side, in addition to this air handling and also the distribution side. Oh, sorry. And with all this, so we can calculate, what is the building loads as our output, with different system, with the energy use of different building systems, and the systems here more means, the lighting systems. And then we can also calculate, what is the energy use for our air handling and the distribution systems. And finally, what is the energy use, for our primary energy systems. So basically, all of these three components will kind of represent, we just kind of sum them together, and it will be the energy use of our whole buildings. Well, at the same time, we also can figure out based on what is the system energy use, and coupled with what is the required building loads to maintain our indoor environment into different status. We can simulate our indoor environment as another dimensions of the outputs, like how the temperature is kind of fluctuating in the indoor environment. And finally, we can do one more step, for that is if we want to incorporate any economic and cost analysis, with certain cost data. Yeah, definitely we can utilize this to support the life cycle analysis in this building energy modeling process. So in building energy modeling, actually we have a different modalities of the models that we typically applied, depending on different application requirements, such as if we want to utilize the building energy modeling for purposes, we definitely want this to be in a very fast computational speed, because we will solve an optimization that requires a lot of iterative calculation. So typically in this time, we want a model with high computational speed, but with a relatively low accuracies. But for the other purposes, it could be reversed. So that's generally for different fidelities of the building energy modeling. And for the low fidelity model, we just utilize the RC model. And for the high fidelity model, and one very common examples here, will be this energy plus model. So it's more complex and dynamic building models that we utilize in this building energy modeling process. And a little bit more details about this RC model. So it's a low fidelity building energy modeling models that we typically utilize in the BEM practice. And it's short for the resistance and the capacitance models. So that it just utilize analogies to the electric circuits in modeling the building dynamics. So that the heat transfer process kind of represented by the interactions of different electric concepts, like potentials, currents, resistors, and the capacitors. And the parameter of this RC model as our building energy model can be either derived from this observed data, or it could be just based on some physical derivations. And specifically for the RC model, it can also be in different complexities. And generally, that's what an RC model that looks like when we utilize that. So this example just shows you, 3R2C models here. So that's for each building components, like this is the wall here, and we will just have 2 capacitors, not per component, so that each of them will represent half of the thermal mass of the wall. And then we will have, 3 resistance here. And maybe this first and the last resistance is more about the radiation and also the convection, while this resistance in the middle is more about the conduction. But the concept here is we're just utilizing these analogies of the concepts in the electric circuits to kind of represent what is the building dynamics and also what is the physical characteristics of the buildings that is here. And you can see that, especially, so this is a 3R2C model, which means that, it's already a little bit complicated, when we applied this RC model. Sometimes we just even applied 2R1C models, so that we just have 1 capacitors per wall, and then we have 2 resistance. So this resistance will have all these convections, conductions, and the radiations all aggregate together, in this resistance as a parameter in this RC model. So that this is a very simplified model with a lot of aggregated physics. So that it's pretty fast in computation. You just have very few parameters that you need to care about, but it's kind of have some insufficiency in terms of its accuracy. And we have certain tools that relies on the RC models to perform the building energy modeling. And one just a quick example that I want to mention here is the EPC calculator, which is short for the energy performance calculator that follows this ISO standard 13790. And we can just input very simplified building geometries, in rectangle, and also some very basic building properties, like what is the U values of the wall, and what is the conductance of the wall, what is the conductance of your windows, and very briefly specify some system efficiencies. Then we will be able to kind of have our building energy simulated. And this is actually a tool that is based on the just on an Excel file. And yeah, maybe I can very briefly show you what it looks like. So yeah, if you are able, to see this Excel tool, let's so just list all the items in this Excel sheet is always required to perform some building energy model, and you just want to specify the climate, and then you want to specify your lighting systems, you cooling and heating plants with certain coefficient of performance, and what is the air distribution system, whether it's a VAV system or maybe it's a constant air volume system, and then some very simplified geometries of your zones, and what is the set points of your indoor environment, and what is the kind of occupancy schedules, and some properties regarding the envelopes here. Then you will be able to kind of perform a very simplified version of the building energy modeling. So you will get the result, and the list sheet I just used for the calculation process. About you will get this result about what is the heating and the cooling needs, and what is the delivered energies to your buildings to meet these heating and the cooling needs in the simulation process. Okay, so let's go back. And a little bit more advanced, I think it's not a little bit, and a more advanced tool that we utilize for the building energy modeling is definitely this Energy Plus, which is a whole building energy simulation program that we utilize to model the building energy use, including all these HVAC systems and the lighting systems, and also water use for our buildings. So Energy Plus represents a dynamic simulation process with much more complex inputs. And then it's just integrated and simultaneously, solve the equations that we have established based on the heat balance for our building zones and also for our HVAC systems. And yeah, it's a heat balance based solutions, and then it can perform the building energy modeling in a really kind of detailed time steps, in a sub-hourly, so that we can also even kind of self-define the time steps we want to perform our energy simulation. Like the minimum resolution it can reach to is about 1 minute per time step for the building energy modeling. And then, yeah, it's utilized the combined heat and mass transfer model so that it accounts for the air movement between zones and also between the indoor and the outdoor environments. And a very important features of that is it will support a lot of advanced manipulations, so that it's such as co-simulation, so that it's especially useful for many research purposes. And this is how the structures of Energy Plus look like, and which is much more complicated, as you can see compared to our RC models as our low fidelity building energy modeling tool. So basically, like in this Energy Plus tool, so the central part of it is it will have 3 managers that is in charge of the surface heat balance calculation, and also our building system modeling, and finally with the air heat balance managers in charge of the heat balance of our air nodes, like in different zones of our indoor environment. While specifically for each managers, they also contains a lot of sub-modules here, and like for the surface heat balance manager, and it has like this sky model modules, so that it will calculate the heat exchanges between our sky with our exterior building surfaces, and it has a shading module, calculates the impacts of shadings, and the daylighting modules to calculate how much light that will travel to the indoor environment, or the window glass module that is about the glass simulation of the energy or the heat that will transferred through these glasses, and also these CTF modules. So this is the calculation of the conduction. So it's the calculation of the conduction transfer. So through our building envelope. And then we also have our building system managers here, that in charge of the calculations for all different types of the loops that you will see for the HVAC system, right? So the air distribution loop, for different zone equipments, for our plant loop, which is our primary energy loop, and also for the condenser loop. And then finally, we will have our air heat balance managers that will kind of have these airflow network modules here to calculate the exchanges in different zones and with between interior and the exterior environment. So let's integrate, they will have we will have an integrated solution manager that sits on the top and calculates all these equations established in all these managers simultaneously. So then it will give us the outputs of our building energy modeling. So this is what interface of our Energy Plus looks like. And then you can see it's not a very user-friendly interface. And it's just actually a text editor. So let's, if you just open up different Energy Plus files, so this will be the stuff or the objects that you will see. Typically it's the Energy Plus file is in a very hierarchy structure, so that each object that will be linked with each other. So for example, you can firstly have objects that defining different materials that it will be utilized in your building construction. And then you also want to specify like a building envelope project that links to different materials as different layers, so that it's a hierarchy structure that the Energy Plus file is carrying. But it's nothing magic here, and you can also open up it just using a text editor. So it's just these different text files and that the Energy Plus simulation engines will read in, and then it will establish the equations and solve simultaneously to come up with the building energy modeling results. Or if you even want to do more complicated building energy modeling, you can even rely on this Modelica, as a language that has its own syntax, and it can be utilized to represent different models. And these days we have been developing these Modelica building libraries, which is open source libraries, with the dynamic simulation models for that we can establish dynamic simulation models for buildings and co-simulated with the district energy systems and also the control systems. But it's just worth it to mention that the Modelica simulation could be really complex and it has a very steep learning curve. So that sometimes it requires you to define a lot of heat transfer parameters even on your own in the modeling process. So overall, it's a very flexible tool, but it's not very widely used in the building energy modeling practice because most of the engineers and they don't need these sophisticated functions, and it will be overshot in many applications. So yeah, this Modelica library is currently under development, and it contains a lot of models or defined components, for all these HVAC systems, energy storage, controls, or you can also put some function module units so that it can co-simulate with the Energy Plus. So for the whole building energy modeling, probably the most popular tools that you will hear, in the practice will be these three, the EQUEST, the IES, and also the Energy Plus. And different tools they have their own features. Like IES, it's a really popular tool in the industry because it has a very good kind of visual capabilities, and you can directly generate a very nicely looking report, to your customers. So it's kind of the most needed functions when you advise your projects. And probably you will hear a lot of other tools, like this Open Studio Design Builder or BOP, which will be related to the project that you guys will do, as the assignment. But for all these tools, these are just kind of the front end of the Energy Plus. that we have utilized as the simulation engines. So basically, this tool just provides you with a graphical interface so that you can draw there, and then on the back end, it will convert what you have drawn into an Energy Plus files, so that the Energy Plus is actually the engine that's utilized to simulate these building energies. And you will also possibly hear some other simulation tool, for the whole building energy modeling, like this Chen, this ESP2, and also DEST. But it's kind of a tool that other people that utilize in Europe or in China, in other parts of the world. Yeah, so we get a chance. Yeah, Michael mentioned that Open Studio is free and open source, and that's why it favors this one. Yeah, that's very true. Yeah, and if you are interested in simulating more detailed aspects related to the buildings, such as you are interested in more microclimate analysis, or the microclimate condition analysis, you can utilize these ecotags. And if you are interested in simulating, more specifically simulating the indoor air qualities, such as in these purposes, you might want to utilize some advanced computational fluid dynamics tools, to check for the indoor air flows. Especially, I think it applies to certain projects like gym. We want to gym for the badminton. We want to maintain the airflow within the gym. In a certain level, you would want to perform a lot of advanced simulations, maybe using these CFD tools like ANSYS. And also Content is another tool that we utilize for the airflow modeling here. Or if you specifically cares about the building envelope systems, then we will also have some very specific tools that we can utilize, like Windows, SEM, or UFI. So you can simulate whether your building envelope will have some thermal bridgings, how thermal bridging will impact you building energy use, or whether your building envelope will have some moisture issues. Then you can simulate using UFI. Or if you want to specifically simulate or design your lighting systems to be better, then you can utilize this DaySim. Or you can, if you want to simulate renewable energy coupled with buildings, you can use these PV watts. So we get a lot of tools, that is existing here, in addition to just the whole building energy modeling tool. And probably at the last, I want to just very briefly introduce this benchmarking, because this will be also related to part of your assignment. So basically, benchmarking is just a process that we use to measure and compare our building energy use, with similar buildings. So that in many practical applications, we would like to compare our building performance with others, so that we will have ideas of what is the energy efficiency levels, whether we consume more or we consume less, compared to other buildings. And also we want to possibly benchmark our simulation results, of our buildings that we want to design. And we want to see, if we incorporate the different features, how our buildings will consume the energy compared to others. So generally, in these cases for the benchmarking, we just either do the direct comparisons with different historical building energy use data that has been collected back. And one very good database here, will be these RECs and also CPECs from the Energy Information Administration collected by the Department of Energy. And they just go out, I think, every 4 years or 5 years. I think every 4 years to just do the surveys and to gather data for the residential and the commercial building energy use with different building characteristics and in different building climates, so that it will serve as a very good baseline for our benchmarking process. And also our benchmarking, in addition to this direct comparison, we can also run like some statistical regression models, so that it will help you predict or come up with a median of what is the estimate energy use of the buildings with certain characteristics, like the number of occupants in different climate conditions. And probably a tool that you will hear a lot, regarding this benchmarking will be these portfolio managers that allows you to do the benchmarking process in a secured online environment. And they have mentioned that this tool has really been utilized a lot, and they already have the data of 25% of the US commercial buildings. And to use the portfolio manager, you can just input very simply, your energy bills, with some basic building properties, like what is the year of the building has been built, what is the square footage, so that it will test you how your building are compared to other buildings with similar climates and also with similar characteristics. And you can also utilize this portfolio manager as a benchmarking tool, as a tracking tool, so that it will help you track different energy and water use in your buildings. And if you get a score, that is above 75, so it's better than at least, which representing that it's at least better than 75% of the similar buildings are nationwide, and it's possible for your buildings to get the Energy Star certified, although it has to be verified by third-party agencies on an annual basis. Cool. I think that's pretty much everything I want to talk about. Because I feel we already running out of time here, but I think the homework and the assignment that Julie is going to send out is related to these BOP tools, which is a tool that I think is very neat and very self-instructed, as the start of you to perform some building energy modeling. So as I said, BOP is just based on the Energy Plus engines. So probably I can just show you very quickly about the interface of that.
BOP, by the way, is specifically meant for residential house use. So that's why we're going to have you try this out in the next scope of work. It's a little bit more of a, just because it's houses, it's a little more of a simple starting place.
Yeah, it will be much simpler, if it's a residential building. So generally, so if you open up the BOP, this is what it will be look like. So that you can choose, this is the drawing interface. So you can choose whether you are drawing a living space or whether you are drawing a garage space. And then if you just draw here, and then it will automatically generate the building energy models, in a 3-dimensional for you. And then you can also choose, for example, after you draw the first floor, and then it will give you options to draw the second floor, whether it's an attic, so that you can just choose the attic, and then just draw it, and then this will be the attic. Or if it's just another story of the living space, so you can also just draw here. Then you will have the options to go to the third floor. So this will be either attic, probably it will be just an attic, or if you want to draw a roof for that. So and then that's the main drawing interface. And then for specific inputs, and you just go to this optional screen. So it contains all the categories that as the major aspects of the building inputs in a very nicely laid out way. So for example, if you have your residential buildings in different types of the walls, you can just go here, and then if it's wood studs, and then you choose different insulation levels as an option here. And definitely you can create your own options by just right click and go to these option managers. So you can add new, right? So you can define your own configurations of your building envelope. And that's about the ceiling, the floor, and also the window as the major components of our building envelope. And then for the airflow side, you want to specify what is the air leakage values. And then you also want to specify what is the space conditioning systems, including both heating and cooling systems for your household. So for some of the system here, so it's kind of mutually exclusive. Like for example, if you just get the air source heat pump, and you will not have the furnace typically installed for your household, so that it's designed in this way. And then for later, you also want to incorporate your water heating systems. What is the set point when you use your HVAC? What is the lighting? What is the appliance? And what are other miscellaneous loads here? Like what is the plug loads? So I think this is a very self-explained tool that contains all the major components, of basic building inputs, in our building energy modeling process. And then if it's a commercial building, it will definitely be much more complicated, but the input channels are typically the same. And then finally, you will go to this site screen so that you can select the buildings in different climates. And you would probably want to download some weathers here, like, for example, if it's Alabama, you just want to download it so that this will give you certain options here, for the simulation. And it can even automatically do some, life cycle analysis for you. But generally, that's about it. And then you can click run simulation, and it will give you some output results. So maybe I can perform a very quick simulation here. Yeah, hopefully it's not too slow. And then basically this will be what the output interface looks like. This panel just tells you different features of your buildings. And then for this, you can just kind of have the output of all this, whether it's source energy or whether it's site energy, or whether it's carbon dioxide emissions that you are interested in. So yeah, I think this is still running, so it hasn't given me the result. But basically, this is the configurations of this BOP. And as long as you have questions, you will always want to go to this BOP here. Oh, sorry, it doesn't allow me to click. Yeah, so basically you can see, how the end uses of your simulated buildings, based on all these specified characteristics of your buildings. And then if you have questions, yeah, just always goes to this BOP help. And then you will find a lot of good information here, I think. So this is about the input channels and different option selection screen, and what does this mean, for each kind of inputs. So this is always a resource that you want to refer to. So that's kind of it, and that's everything that I want to briefly introduce about building energy modeling and also this BOP tool.
Fantastic. Thank you, Dr. Chen. That was quite a crash course in building simulation. So appreciate you getting through all of that. I'm gonna say thank you, I think, and wrap up class for the team. I appreciate you guys accommodating the schedule shift today.